Hello everyone, welcome to my presentation. The title is Diversity versus Parallelism in Distributed Computing with Redundancy. My name is Pei Peng. I'm a PhD student in Rutgers University. This work is with my advisor Amina Sujani and also with Professor Philip Whiting. As numerous machine learning and other algorithms increase in complexity and data requirements, distributed computing can provide parallelism that provides simultaneous execution of smaller tasks that make up a larger computing job. However, the large-scale sharing of computing resources causes random fluctuations in task service times. Redundancy here can provide diversity so that the job is completed as soon as any fixed size subset of a task has been executed. Here we give an example to explain the distributed computing. In the example, Bob has to finish his homework before the deadline. He's smart, so he finds his friend Alice to help him. He splits the homework into part 1 and part 2. So Bob does part 1 and Alice does part 2. However, distributed computing is not always fast because of the straggling jobs. In this example, Bob does his homework very fast because of the deadline. Alice, she may not familiar with the material, so she spent much longer time to finish. But Bob has to wait until he can hand in all of the homework. Redundancy, in form of task replication and erasure coding, can help to mitigate the straggler. Like in this example, Bob, instead of just find Alice to help him, he can also find his friend Eve. In this way, Bob does homework part 1, and Alice and Eve does homework part 2 separately. Then, even though Alice needs to spend much longer time to finish, if Eve can finish the part 2 fast, Bob can hand in his homework early. However, replica doesn't always help. Like in this situation, if Bob himself does the homework very slow, even though Alice and Eve finish their work very fast, Bob has to wait a longer time to hand in his homework. Erasure code is a potentially powerful way to shorten the job execution time, especially in previous example. However, it can only be used in some specific scenarios. Because like the homework, we cannot always encode the homework. But if Bob does some matrix multiplication homework, so what he can do is he split the matrix A into A1 and A2 and assign them to Bob and Alice. And for Eve, he can use the A1 plus A2 as the matrix to time the B. In this way, any two of the students finish their work, this homework is done. Let's see this example again. Even though Bob does his own part very slow, but Alice and Eve do their part very fast, then Bob can still hand in the homework early. Now we can introduce the definition of diversity and parallelism. The diversity and parallelism are defined according to the redundancy for each job. Diversity increases with redundancy, and the parallelism decreases with redundancy. Let's see in this figure, redundancy to the left is decrease, to the right is increase. If the redundancy decreases to the minimum, that's splitting. It's shown in this example. Bob split the homework into part 1 and part 2. And the redundancy increases to the maximum, that's replication. Let's say this example, the Bob assign the whole homework to himself and also Alice. What is the trade-off between diversity and parallelism? As we know, both parallelism and diversity are essential in reducing job service time, but compete for the system resources. Here we compare the replication and splitting. The task execution time for replication is TR1 to TRN for worker 1 to worker n. And for splitting, it's TS1 to TSN. When we consider about the comparison between each task, we know that the task for splitting is normally smaller than the task for replication. When we consider about the job completion time, what we get for replication is the minimum of TR1 to TRN, but for splitting, we get is the maximum of TS1 to TSN. Then we cannot decide which one gives the minimum time. And we also know that the coding is in between of replication and the splitting. So the trade-off will be which strategy is better, replication, coding, or splitting. And if it is coding, what's the code rate it will be? To formalize this trade-off problem, we should answer the following questions. First, what distribution has been used for job service time? Second, how the distribution changes with the task size. Before answering these two questions, let me introduce the system model and the prior work. The system model is the standard master-worker system. In this figure, we have one master and 4 workers. Jobs can be split into tasks, which can be executed independently, in parallel on different workers. Here we provide 3 jobs. Job 1 is executed with splitting. Job 2 is executed with replication, and the shadings are replicas. Job 3 is executed with 4.2 erasure code. The shadings are coded tasks. We can see that based on different redundancy, the job size is also different. In this paper, we consider the expected execution time for each job. To model the task size, here we introduce the concept of computing unit, CU. We know a fact that job cannot be split into any size of tasks. In the example, for homework, the smallest task should be a question. And for the matrix multiplication, the smallest task can be a vector of matrix A times matrix B. Then we know that a job consists of tasks and each task consists of CUs. In these slides, we list all the parameters and notations that we used in the paper. Here, I only want to talk the first 3 parameters. N is the number of workers. To make this problem simpler, we assume that this N is also the number of CUs in a job. For the K, it decided how much redundancy we introduced, because the K over N is the code rate. For S, it is the number of CUs per task, and S equal to N over K. The rest of the parameters we will introduce later. Here, I list all the references that we used in this presentation. Now, we can try to answer these 2 questions. First, what distribution has been used for job service time? For theoretical analysis, shifted exponential, Pareto, Erlang, and bimodal were used in different papers. In this paper, we assume the service time per CU is shifted exponential. It shows that the service time V equal to delta plus X, where delta is a constant modeling the minimum service time. It's also the deterministic component of the distribution. X is the exponential random variable, which modeling the straggling. It's also the random component of the distribution. The other distributions we mentioned here are analyzed in our journal version of this paper. The second question, how the probability distribution skews with the task size. There is no consensus on this question. Some papers skew the random component. Some papers skew the deterministic component. These papers provide the scaling for specific distributions, like shifted exponential, but none of them provides a model for general distributions. Here we give an example to explain these two models. The service time for each CU is shifted exponential. Then the task execution time y is, for scaling the random component, y equal to delta plus s times x. Here, this s is the number of CUs per task. It also means the task size. After answering these two questions, let's see some prior-related work. We can classify the relative references into two categories. The first category, there are many papers working on designing codes for given systems. For example, paper 5, 6, and 8. However, they do not focus on optimizing code rate. The second category, there are few papers working on how much redundancy should be introduced. For example, 9, 10, and 11. However, paper 9 and 10 only focus on applying replication in queuing system, and paper 11 only focuses on Pareto distributions. Now, let me introduce the task service time scaling models in this paper. Here we have three models. The first model is server dependent, which is the same as the scaling the randomness, which we introduced before. The delta is some initial handshake time. Xi is the service time for CU on server I. And S is the number of CUs. To better understanding this model, let me use the Bob and Alice example. It is easy for Bob to get help from Alice and Eve, but he needs to spend some time to ask them. When the students start doing the homework, because the problem in homework is very hard, sometimes they need to spend much longer time to finish one problem. Then the straggling effects depends on doing the homework. The second model is data dependent, which is the same as the scaling the deterministic component. In this model, the service time for CU is delta, and the Xi here is the system randomness. Let me use the Bob and Alice example again. This time, Bob has to persuade Alice and Eve to help him. He may need to spend a much longer time to persuade one of them. So the straggling effects depend on the persuading. When the students start doing the homework is very easy. So each problem only takes them a constant time delta. The third model is additive model, which is very natural. We assume the execution times of CUs are independent and identically distributed. Then the task execution time equal to the sum of service time per CU. Although this model is very natural, comparing the other two models, it is very hard to analyze. Next, let me introduce some main results in our paper. In this table, we list the optimal strategy for different scaling models. For the server-dependent model, it is always good to use replication. For data-dependent model, at the increasing of straggling probability, we should use from splitting to replication. For additive model, at the increasing of straggling probability, we should use from splitting to coding. First, let me introduce the results for server-dependent model. We can get the expected job completion time from theorem 1. Also, from theorem 1, we can prove this expected time is minimized by replication or maximal diversity. Let's see some numerical results. This figure shows the expected job completion time versus K for different scenarios. From this figure, we have two conclusions. First is the replication of maximal diversity is always optimal. Second is the replication is much more effective when the W over delta is large and has less payoff when W over delta is small. Here are some results for data-dependent model. The expected job completion time can be get from theorem 2. By taking the log approximation of harmonic numbers, we find the optimal K star, which minimizes the expectation. Also from the theorem 2, when the delta is much larger than W, the execution is essentially deterministic. It is optimal to use maximal parallelism. When the delta is much smaller than W, the execution time is much more variable, and it is optimal to operate with maximal diversity. Here we also have some numerical results. From the left figure, we have three conclusions. The first is replication is optimal when W over delta is very large. The second is splitting is optimal when W over delta is small. Otherwise, coding with a certain non-trivial rate is optimal. So far, the results for server-dependent model and the data-dependent model are interesting, but they are not hard to get. For additive model, it is not easy to derive the results. In this slide, we compare the replication and splitting. For replication, we can get the expected job completion time by theorem 3. The equation here, it seems very complicated. The proof uses the birthday problem analogy in paper 12. For splitting, we can also get the expected job completion time. This is easy to get. The equation comes from the largest order statistics, since each worker has only one CU. After knowing the equations of both strategies, we can get the lemma 1, which tells us that for n sufficiently large, splitting outperforms replication. And next, we compare the half-rate coding and splitting. Here we consider a special case when delta equal to 0. Then the service time for each CU is exponential. We can have a theorem 4. Suppose that n is even, then the expected job completion time for half-rate coding stochastically domains the time for splitting. Overall, we can have a conclusion. For a system with exponential service time and sufficient large n, half-rate coding is better than splitting, which is also better than replication. Notice that our conclusion has two limitations. The service time distribution is memoryless, and the conclusion only works for code rate is 1/2. From the numerical result, we can conclude that splitting is optimal when W over delta is small. Coding is optimal when W over delta is large. And half-rate coding is better than splitting when delta equal to 0, which is consistent with theorem 4. Finally, even n equal to 12 is sufficiently large that satisfies the lemma 1. Our results are concluded in the table 1, and this table also summarizes more general results reported in the journal version of this paper. For better guidance, we provide some conjectures and conclusions for general distributions.